Welcome to the Bug Bash podcast, where we talk about all things software correctness and reliability. I'm your host, David Wynn. Software testing research is exploding, but in practice, most companies' testing approaches seem stuck in the past. Where does that gap come from? It often boils down to the distance between academic promises and the practical needs of developers who need usable tools and fast results. In this episode, I talk with Rohan Padhye, head of the PASTA research group at Carnegie Mellon University, who has lived on both sides of that divide. We explore how fuzz testing crossed that chasm from industry curiosity to academic focus and back again, and what it will take for other techniques to do the same. Rohan shares insights on designing testable software, building a robust testing culture, and what truly makes a good property for finding bugs. If you're interested to hear about crossing the gap between testing theory and testing practice, stick around. Rohan, thank you so much for being here today. Would you care to introduce yourself a little bit?
Hey, thanks for having me. I'm really excited to be here. I'm happy to introduce myself. So, I'm a professor at Carnegie Mellon University, where I lead the PASTA research group. So, PASTA stands for Program Analysis, Software Testing, and Applications. So, we do research on all things software testing and debugging. Everything from fuzz testing, property-based testing, root cause analysis, and testing, complex concurrent and distributed systems. And I also teach classes on program analysis and bug finding here at CMU.
So all the fun stuff, right?
Absolutely.
What got you into it, if I might ask?
Well, I like to do research on topics where I'm my own customer, and I am I'm a world expert in writing software that has bugs. And so it's always fun to do research on building tools that can help people like myself in developing software that's of higher quality, reliability, and security.
Yeah, you might want to check the leaderboards on the worst software developer, because I might have you beat, or at the very least, I'm sure there's an LLM that's giving us a run both for our money, right?
Absolutely. I think that's becoming, that's a hot topic for research in this field as well.
I would imagine so. Well, so you've got a bit of a foot in the academic world and in industry as well, having worked on some real world projects and explored some of the avenues in that direction. Talk to me a little bit about what's the state, would you say, of PASTA, which is now what I'm going to call it PASTA, because that's now going to be my new favorite way to describe it. What's the state of PASTA, would you say, in academia and in industry?
Sure. Yeah, that's a good way of putting it. I think, both in academia and industry, there's obviously been a lot of focus on developing, really cool new tools for finding software bugs automatically. I think one of the main sort of differences is that in industry, I've seen a lot of focus on developing very usable tools. So things that software developers can get started with really, really quickly and get using without having to do a lot of sort of configuration or a lot of sort of manual work, and tools that work for a large number of target programs and can find lots of bugs really quickly and give you like concrete results. Like, here's a bug that you can fix. Here's an input that will trigger something bad in your program, and you can go fix it. Academic research has, in this field, has come from many different directions. Decades ago, there's been a lot of research on formal methods for program analysis, everything from formally trying to verify properties about a program, in some cases trying to prove programs correct, or symbolic analyses that can help identify exactly under what conditions a software bug might trigger, as well as from the field of software security. There are techniques for sort of uncovering specific kinds of software bugs, things like buffer overflows or SQL injection attacks. And a lot of the focus in the academic techniques has been on the algorithms in terms of like how well can we actually find a particular software bug, or for a given set of programs, how many bugs can we find in a given amount of time, or if we were trying to validate some software, what guarantees can we give about that software's correctness, security, or reliability after we have run some tools on it. So it's much more about these sort of meta questions about how well we're doing, rather than in tool building. And so when you talk about the pasta research group, which is the main, the set of folks who I work with at CMU, we actually try to look at topics that are somewhere in the intersection of these two, different approaches. And so we're looking at not only new algorithms and methods of finding bugs, but also thinking about platforms for folks to actually run these tools and find software bugs and issues in real world software.
Man, every time you say pasta research group, I'm going to be really thinking hard about how to improve spaghetti.
Yeah. Our research group actually has a motto that says, "We're not afraid of spaghetti code."
Excellent. All right. So I hear the two different conceptions between academia, their focus on algorithms and such, and in the industry where the focus seems to really be on time to value and expedience. What my brain almost hears that as fancy versus not fancy, because that's what we would say where I'm from. What do you think drives that between those two different arenas?
Yeah, it's a good question. So I think there's a couple of different things. One, I think, is incentives. So of course, in the academic world, and I'm saying this as an academic, and it's a sort of reflection of my own community. But like, it is sort of true that in the academic world, right, you get these brownie points or beans, as someone would say, right, if you're one of those who count beans, for coming up with sort of these new ideas, new algorithms, something that's fancy that makes you look smart. In some ways, you want lots of plots of lines going up and showing that one technique may be better than the other. So it's sort of an intellectual pursuit to try and come up with really good techniques and algorithms, or maybe provide some guarantees. Whereas in industry, I've seen that the incentives are different, right? The incentives are, how can I find what I'm looking for, which in this case might be software bugs, in the shortest amount of time, in the most cost-effective way, given that both compute and human time is sort of expensive and limited, and so what can I do quickly, and how do I get results that are actionable, right? How do I get results where once I find something, I can quickly go in and sort of fix it? And so one aspect, I think, is sort of just the incentive structure, in sort of the two communities.
But at the same time, the Venn diagram's not zero, right? Those aren't two independent circles. So what are some good examples of things that have crossed the chasm, that have made their way into industrial practice?
Yeah, so I think a lot of the research in the field of fuzz testing is very interesting. Fuzz testing is now a super popular sort of technique for finding software bugs. So for those of our listeners who are not familiar with this technique, it's simply a way for finding software bugs by randomly generating inputs to a program and just trying it out and just throwing random inputs at the program many times, maybe millions of times a second, until one of those inputs causes your program to crash or abort with some sort of undesirable behavior, which reveals a bug. It's a very dumb technique. It's been around for many decades, but being a dumb technique, it's actually been very successful. There were folks fuzzing for things like buffer overflows for many decades, but I think the field really took off around 2014 or 2015 or so, when security researchers at Google released these sort of open source fuzzing tools. One is called AFL, which stands for American Fuzzy Lop, and the other is called LibFuzzer for LLVM. And these were tools that were doing something called coverage guided fuzzing. So they were doing random input generation, but also did some lightweight program instrumentation to check how much of your code is being exercised when you do these random testing. So this technique is really, really powerful. Many of these large tech firms now have invested quite a bit on fuzzing infrastructure that runs fuzzing tools on large security critical software like web browsers and database systems, and they're continuously fuzzing, almost as you do continuous integration with unit tests. Fuzzers are continuously generating trillions of inputs, I guess, on a weekly or monthly basis to find the latest security vulnerabilities and then the latest releases of the software. So this sort of came out from industry, of course, but academia picked up on it quite a bit. And the reason is that this is a technique that actually has a very rich space for potential algorithmic improvements, right? Because all you're doing is you're doing a random search on a very large space, right? The space of all possible inputs it sort of grows exponentially with the size of your inputs. In many cases, it could be infinitely large if you have an unbounded input. There's a very large search space. There's no hope in going through all of the inputs. There's no guarantee that you will find all of the bugs. But there is a limit in how much time you have to search through the space. And so that gives academics a lot of opportunity to come up with many different algorithms, many different techniques to try to do the best in a sort of given amount of time, right? And so there's actually been, since 2015, I used to track this at one point, but initially, if you look at the top research conferences in the field of like security and software engineering, around 2015 or so, there used to be some people doing research on fuzzing, maybe about, say, 2 to 5 research papers a year. By around 2020 or so, there were about, somewhere around 200 or so research papers with like fuzzing or fuzz testing in the title, right, being published. So a lot of researchers picked up on this technique as a place to sort of study how do we make algorithmic improvements. And to the credit of the folks who are using these tools in industry, they have been receptive to a lot of the techniques. So there's this a tool now called AFL++, which is a community driven fork of Google's original AFL tool. And so it's open source, and there's the beautiful community around it. And these open source developers have incorporated a lot of the techniques that academics have developed, have written research papers about, and incorporated into this fuzzing tool, which is general purpose, easy to use, and now is actually being used by many folks in industry to find real software bugs. So it's a real nice example of that intersection that you alluded to.
Awesome. So there's a level of intuition that does want to push back against fuzzing somewhat, right? Where it can't be as easy as just flipping the bits randomly and then making something go wonky. And even if it was technically that easy, surely there is such a large search space. If I take any degree of structured input, whether it's a JSON or XML or a SQL statement, right? Like, I can barely parse SQL in my own head, let alone letting some sort of random generator come up with that. There's a level of intuition that wants to push back on that. But clearly, there's been a lot of success on the other side as well. What do you think's the rejoinder to that first pushback on intuition?
Yeah, that's a great point. I think I'll say two things about that. One is that this intuition is not completely wrong, right? So a lot of, especially when you're testing things like database systems, you alluded to is SQL. It is true that if you just start flipping bits at random, the probability of you coming up with a valid SQL query is very, very low. It's vanishingly small. And even if you come up with a valid SQL query, and if you are testing a specific database, like having some semantics to go along with what is a valid table, like how do you perform valid joins, etc., it's virtually impossible to come up with anything reasonable if you just start flipping bits. And so there definitely are a lot of tools that take into account like domain expertise, right? Things like, let's say, the structure of your input syntax, like a grammar, maybe some information about your domain or your semantics in the case of like the database fuzzing, or maybe even some smarter forms of feedback. So not just looking at things like code coverage, but looking at what parts of the application that I'm testing, what kind of signals from the application are important to me for my particular testing objective. Like if you're testing like a database, you might want to think about like, am I actually performing joins successfully? Am I actually returning non-empty results, or am I returning nulls? So things like that could actually be useful signals. So there actually has been a lot of success in tools that take into account some of this domain knowledge. But on the other side, I would also say that, with some caution, that there definitely has been, in some cases, a lot of work put in to try to like, use this intuition and then think about, maybe we can, use even more sort of fancy math and symbolic techniques to try to understand exactly what my input should look like for a given problem. And I think that that sort of approach can sometimes, lead to some kind of like roadblock. So, I always think about this a short essay called "The Bitter Lesson," written by Rich Sutton in the field of AI. It's a nice essay. You can go look it up on the web. It's about the the progress in the field of artificial intelligence, and how for decades researchers have been devising techniques for things like natural language processing, thinking about like tokenizing words, and like computer vision, trying to identify like edges in your to identify shapes, and other sort of rule based techniques for solving problems. But the bitter lesson is that often the techniques that actually won out in the end were like really these dumb techniques based on like neural networks and matrix multiplications, right? And that's what we're sort of using today for most sort of AI applications. And the reason for that is because the simpler the technique and the more sort of clean and in some cases even dumb that the technique can be, it's actually amenable to scaling as our compute capabilities and strength of let's say compute chips or compute capacity keeps going up over time. And so even though the search space sometimes seems large, and it seems like random flipping of bits surely cannot really make progress, it's much faster to scale something by saying I'm going to flip this bit randomly a bazillion times a second with tens and thousands of let's say CPU nodes, and let the technology evolve and just leverage the raw power of compute, than trying to spend a lot of human capital and trying to be extremely smart and extremely fancy in embedding too much of domain logic, which sometimes can end up not scaling as well with sort of more compute. So for example, if your symbolic technique is not easily parallelizable, that can end up being less competitive compared to a dumb random search, because you can flip bits in parallel. It's an embarrassingly parallel problem, right?
Yeah. I almost see a parallel in analytics in the sense that there is a lot of thought put into statistical techniques in the absence of a full population, right? And then once computing power grew enough to the point where, well, why don't we just put all the population on a hard disk, or like a lot of hard disks? And then it became much less about how cleverly we could compress the problem down to a computable space, and much more about, well, how do I just make sure that I counted everything across 10,000 hard drives if one of them fails, which is a very different problem space, right? Gotcha. Okay. So, well, talk to me a little bit more about some of the work that you've done, Rohan. So you've done a lot of different things across the different projects that you've worked on, and some of them change the targets of the fuzzer. Some of them change the priority of where things like go. There's a lot of different interesting things that you've tackled. What guides what you think is interesting to work on next?
Yeah. So I'm, as I said before, I'm looking for ways in which we can still, leverage this power of, dumb techniques, things like, just raw compute power and like random bit flips, but also allow, the users of these tools like, fuzz testing tools to provide some sort of domain insights to make this dumb search a little bit more effective. And so some of the research that I've done, I've built tools like JQF, which is a Java-based fuzzer, uses ideas from the field of property-based testing, it came out of the functional programming language community, where instead of just flipping bits at random in an input file, you can think of synthesizing well-typed inputs for a given data type, but doing that sort of randomly, right? And so you can sort of say, give me a random input of a given type. And then, the work that I did was a combination of ideas from the world of property-based testing, where you have some information about your data types. In this case, it could be like, we talked about database fuzzing. You might have some type that represents a SQL query. And then you might want to say, can I instantiate random SQL queries? And then still use the power of something like coverage-guided fuzzing to provide the random search some sort of guidance of what to look for next, or what has already been found, and what's sort of the direction for new information. And so this combination is really powerful. And so we call that technique semantic fuzzing, because it helps us go beyond just trying to recreate the syntax or the structure of inputs, but actually go and search over various behaviors that test the semantics of the actual program that you're testing. And so that was sort of one phase. We did some other work on allowing users to customize the guidance. So, which means that apart from code coverage, if you cared about other kinds of signals, so for example, you may want to find performance bugs, and so you might want to say, can I, get inputs that actually cause my program to run really, really slowly? And so you can actually count, how long does it take for, my program to run each input, and then we can now, come up with fuzzers that help you find worst case complexity bugs, right? And so, I guess to sort of zoom out, when I think about working on these projects, I'm trying not to rock the boat too much, right? I'm trying to still be able to leverage the power or the simplicity of something like random search, but also try to provide users with more control. So this is some stuff that I've worked on in the past. Currently, my research group is focusing on concurrency bugs quite a bit. So we recently released a tool called Fray, which is a concurrency testing platform for the JVM. And here again, our philosophy has always been on focusing on tools that work. So more than thinking about really, really smart algorithms, we focused on building really, really good platforms that we know will work on real world targets. So we build tools that can find concurrency bugs in very well tested targets like Apache Kafka or Apache Lucene. And then we said let the academics figure out all the algorithms, but what we really want is platforms that are usable, that work, and that they are efficient.
Stuff that just works the first time, as my wife would phrase it. Yeah,
absolutely.
So you mentioned Kafka, you mentioned Lucene. As you turn Fray and other tools on them, what would you say has surprised you the most about them?
I'd say what's surprising is sort of the gap between what academia has been promising for decades and what and what tools the developers of these really mature projects actually had available to use in order to ensure their software was reliable. So we looked at bug repositories of some of these projects like Kafka, and you'll actually find lots of issues that talk about things like flaky tests or like non-reproducible behavior or these things called like Heisen bugs, which are like bugs where once you try to add debug statements like print statements, those bugs go away, and so they're really hard to debug. And if you sort of look through those issues, what we found was in many cases, the way that developers were testing these targets was simply like running concurrent unit tests in a loop. So you have like a unit test that, let's say, spawns multiple threads, does some work, waits for those threads to join, checks that the result is okay, and then just says, let's run this test like 1,000 times and see if we find anything. And so this is like just trying to hit a very tiny nail with a very large hammer. And so what happens is that you're not sort of guaranteed to be able to reproduce any sort of funny behavior that you might see with this kind of technique, and there's sort of no real way of controlling which thread runs at what point, and so you actually might be searching at the same place in every iteration of your loop. And so what was surprising was that things like concurrency testing are really old problems, and academics have been researching ways to find concurrency bugs for, I think, longer than I have been alive, to be honest. And yet, the tools that are available for everyday developers just don't exist with the same with the same level of I would say quality or the kind of guarantees that we would expect or hope to find after all of this research. And so what we really worked on is platforms that would enable developers to make use of all of those fancy algorithms that people have been working over decades, but that actually works on these kinds of targets.
So I'm going to interpret that as it's amazing in some sense how far we can get without more sophisticated tooling, but there's probably a lot of toil that we could have avoided at the same time if we can adopt some of these newer techniques, because while some of the more traditional techniques with example-based testing and the like might be a way to create something out of nothing, which is amazing because that's what creation is and is good stuff. But at the same time, it's not the best way It's like shining a lighthouse through or a flashlight through a dark room. You're going to find where to put your next foot, and you're not going to necessarily know what is all in the space around you. And if anything wobbles inside of the program that knocks it on a different path, it can lead to 1,000 paper cuts in different directions, as you mentioned, right? So it would probably behoove a lot of these projects to pick up something more modern. Is that right?
Yeah, absolutely. I mean, like reproducibility really is key, right? I mean, like a lot of these tests, for example, ideally you would want to run them in, CI, right? After every code commit, and you would want your CI to be reproducible. And you also would want, any bugs that you find to be debuggable, right? By, so that you can actually get to the root cause. And so, yeah, I think these things are really important. And we just need the tools to be able to do it.
Yeah, we're going to have to add on CF to CI/CD. So it'll be CI/CD, CF for continuous fuzzing, right?
Continuous fuzzing, absolutely, yep.
All right. So let's say there's a number of different people that might be in the audience. I'm going to ask you, Rohan, for a suggestion for each of 3 different types of people that might be listening today. So if these 3 people wanted to improve their testing posture in some state, what sort of advice would you give to a brand new developer, a senior developer, and an engineering leader or VP, what have you? Feel free to take those in any order.
Yeah, I think for let's see, I would say like for someone who's like a junior developer or someone approaching testing a sort of non-trivial system for the first time, I would say do not underestimate random. It's random testing is sounds really dumb, and it's not the first thing that you might think of when you're sort of trying to write tests, right? Because it's very natural to think about coming up with edge cases, you sort of yourself, and trying to be really careful about the kinds of tests that you write. But like in many cases, just having some source of randomness, whether it is as simple as doing cat/dev/random and just like throwing random bits at your program, to just simply writing a property-based test that allows you to, invoke some function in your program with random inputs. That goes a really, really long way before you use any sort of other fancy tool. Just try, random inputs. I think everyone should do that. I think every single, new code commit, a new patch that anyone, submits should have some sort of like random testing, to ensure that that code can be validated really, really quickly without any, additional sort of tool support.
Yeah, which also might be doubly good because most junior developers may not. Actually, I was going to say they may not have developed hubris yet, but that might actually be the opposite. Anyway, continue, please.
For a senior developer, my suggestion would be mostly to just think about ensuring that a software system is testable and sort of well designed for other tools to take advantage of things like draw compute power from a random search, right? So often what we have seen is that there are even when there are tools available that can do things like random fuzzing really well, even when you can provide domain insights, some of the challenges that these tools face are due to sometimes the sort of the design of a software system that let's say maybe does not provide any APIs for doing any form of like stateless testing or any form of sort of clean debugging. And so I think just having software systems be designed such that they have clean entry points for testing, that have clean and sort of well specified oracles for deciding if a given behavior is desirable or undesirable, goes a long way in making all of the tools that are available actually useful in practice, because the tools are not going to figure that out magically, right? So the tools can search over inputs, can give you good edge cases to try, but the software needs to be able to sort of figure out that an edge case has been triggered and sort of tell the user when something bad happens.
So I hear you on that one. You said clean oracles. What format would you imagine people would be storing their clean oracles in? Because I almost view this as a specific to a more general problem of how do we clarify the intention of what we have for the software that we're building to the actual implementation of it. Oracle is one way to do that. So would I generalize or specify in what you said in the sense of, do I need to build an Oracle over here, or is there some other form of intention specification? I'll find better words for it later. But is there some form of intention that you would say needs to be stored at some level in order to make the most of these testing techniques?
Yeah, I mean, that's a good question. I mean, the test Oracle problem is probably one of the hardest problems in software all of software engineering. I might even go that far to say that. And so there's just like no magic 8-ball that will like spit out test oracles for you. Of course, again, there's been a lot of research in this space, and there's a lot of techniques that will help you identify certain good properties that your software might have. But it's hard, and so it's mostly a mix of the experts coming up with good specifications and writing tests that have encoded a software's intentions. Of course, you can use your favorite AI tools nowadays to help you with that in many cases. But also, I think one thing that people often overlook is that there are many forms of test oracles that you can actually get for free, and you don't actually have to write down. So there are approaches to testing like differential testing, which is like trying to compare the behavior of two software systems that should ideally be identical, and then if there's any variation, then you sort of flag an issue. There's things like metamorphic testing, which is where if you sort of change your input slightly. So given one input, if I change it slightly, I have some expectation of how the output of, let's say my program should also change correspondingly. And so you could sort of write an, oracle that says, if I, have some idea about, how my program is invariant to small changes in the input, I can actually check that the output doesn't, go completely bonkers when I make this sort of small change. And I would also say, just having to design or write property-based tests actually forces a lot of people to just think about their software in a very different way. You sort of try to come up with good properties to check that. Sometimes these sort of oracles sort of come out naturally from just that exercise of having to think about what properties a particular function should satisfy.
What is a good property to you, Rohan? What should we be aiming for when we go in that direction?
I think a good property is one that actually gets violated when you have a bug in your code, right? So I think what we want from our property is something that actually gets violated when you've sort of made a mistake. And that's a little, sort of backwards to think about sometimes.
Yeah, that cheats in my head. No, don't say that. What's a better way to phrase that I could use? It's like, yeah, my software works when it does the right thing. It's like, yeah. So
right.
If I'm writing a property, what am I looking for? What distinguishes a good one from a bad one? Sometimes I will say that a typical example-based test is a property just for the tiniest narrow possible pathway that you could walk. And I would assume that's not what you're thinking of when you're thinking of a good property. But you could also go really general on the other end of it, right? You could just, not crashing is a property, but it's so high level as to be a little not very informative in the domain that we're working in. So if I have a domain of some kind that I'm working in, what feels like a good property in your eyes to target?
A good property is something that also sort of clearly expresses intent and can sometimes serve as just documentation for the program's specification. And so I think one way of thinking about properties is, most well-designed software already has some documentation of like, what a, let's say, particular piece of code should do. It's usually written in, natural language. Just trying to formalize that and just to say, I've done a thing. Can I check that it did the thing that I said it was supposed to do in terms of results, in terms of especially error cases? I think good properties do check for error cases. What happens when my input is ill-formed, or when something that I expected to be there in input is not there? I think goes a long way in helping catch bugs really quickly.
So, as an academic, as a teacher, why do you think that we don't see properties being taught as the default way? to learn how to write code and to create systems? Because it certainly seems like there's a lot of leverage inside of it, but the typical approach has much less leverage. Why does that tend to be the default?
So I will start off by saying that when I teach programming, I do talk about properties. But let me say, why it doesn't necessarily come naturally to a lot of people who are just, learning how to write tests. I think you're right. Example-based testing is definitely the default. And my view, and this is based on, teaching, undergraduate students about the foundations of software engineering for several years now. I think my view is that so junior developers, when they're writing tests, they're often trying to express what their software should do in terms of examples, because that's what they have designed their software to do. So they're sort of used to thinking about the use cases for the software that they have developed intentionally. I think what we're sort of missing in many cases is this notion of adversarial thinking of like, where will my software go wrong? What are the edge cases where the thing that I've built will actually break? Because most people who write software for the first time aren't thinking about why it might be bad. They're thinking about why it might be good, because they actually have spent time in trying to solve a particular problem. And so they're really excited in, they want, if at all they, are excited in writing tests to the extent that they are excited in expressing the intended behavior of the software that they have successfully actually implemented, and to show that it sort of, demonstrate that it works, right? And so example-based testing comes naturally because it's demonstrating sort of the positive use cases for the software that has been developed, whereas property-based testing and fuzz testing often helps users uncover edge cases for things that they have not really considered, and that requires a certain level of adversarial thinking that comes naturally to people who are either trained in something like software security or maybe even other sort of engineering disciplines where you're sort of always thinking about the worst case. But if that's not sort of your if that's not your first intuition, then example-based testing just becomes like a way of demonstrating, hey, here's what I built, and this is how it works.
I often wonder if it's because there's a little bit too much trust in the fingers to translate correctly into code what the mind expected, in the sense that there's just, sure, the machine could do a bunch of things, but I told it to do the thing that I wanted it to do. I don't have to worry about, sometimes I think about properties in terms of boxing in the right behavior or boxing out the right behavior. And that's just not usually the way to get from 0 to 100, or to get from 0 to 1.0, excuse me, or maybe 0.1, depending on how you want to define it. Usually it comes out with a bit more of, I need to focus on the thing that comes out. Right? Am I thinking of that right?
Sure. Yeah. I can see that. Yeah, absolutely.
Yeah. All right. Well, I have not forgotten about our VP of engineering, who I'm sure is on the edge of their seats to figure out what the recommendation might be from Rohan. So Rohan, if a VP of engineering wanted to improve their testing posture, the state of the testing in their organization across, a number of teams, what would be a recommendation you have for them be?
I think for a VP of engineering, my recommendation would be to just invest in a sort of culture of testing, and that may be, different depending on the kind of organization or the kind of software. But like, as an example, you mentioned, a term like continuous fuzzing, some time ago, and I think that things like that should be taken seriously, right? And there's even been proposals I've read online for things like fuzz-driven development, where the idea that if you were to, produce, let's say, a new pull request or a patch that you're submitting to some code base, then you should also accompany it with an example sort of fuzz test and an entry driver, such that when you run a given fuzzing tool within a certain amount of time, you are actually able to that particular tool is able to find an input that distinguishes the old behavior from the new one, so that it can sort of detect those kind of regressions, right? And so that may be taking things to an extreme, but I think in general, this kind of thinking of like, how do we think about testing as a sort of a first class, not just testing, but how do we think about automated testing with advanced tools like fuzzing tools as a first class activity in not just the software design, but in the entire design of our overall process. think incorporating that into the overall culture, thinking about adversarial testing all the time, I think could go a very long way.
Awesome. Well, Rohan, that's about all the time we have for today. Thank you so much for coming on the show. And to everyone else, has a good day. Thanks for checking out the Bug Bash podcast. If you want to reach out, maybe with an idea for the show, or maybe you want to be on it, send us an email at bugbash@antithesis.com. Or if chat's more your style, head over to antithesis.com and scroll to the bottom where you'll find the link to our Discord. Until next time.